This is the second part of the probability review on page 19 of your diploma review notes. So we started with probability, looking at the basic types of probability and how to calculate odds. Now we are going to move into the probability of A or B and the probability of A and B. So there are four different formulas on your formula sheet, and each one of them have a different meaning. So let's talk about the word or first. Or can have two different meanings. You could have two events that are mutually exclusive, which means that they have nothing in common, in which case the formula just says that you add the probability of those events together. You could also, so for example, the probability of rolling a 6 on a die or a 5 on the die, because they cannot happen in a single trial. Okay, you can also have non-mutually exclusive events in which you would have common elements. So we looked at lots of examples in this involving cards, right? For example, picking a 7 or a heart. We know that those are non-mutually exclusive because you can pick the 7 of hearts. So then that's when you would use this formula. Okay, we also talked about the word and. The and word always means multiply in Math 30-2. So then it's a matter of, does the first event affect the probability of the second event? So independent means that the probability of B does not change based off of what happens in A. For example, if you are picking a card and then you replace the card and pick another card, they are independent of each other. Whereas dependent means that A affects B. So we have taken a card out, and this time we did not replace it. I just want to remind you that in this formula, probability of B, given that A has already happened, this is not a division sign. This is just a probability of B, given that A has already happened. So you can almost ignore that divided by A piece if you're aware that they are dependent, sorry, not divided by A, the given A, if you're aware that they are dependent events. So mainly remember here that we're talking or means that we're going to add the probabilities, and if we're talking and, it means we're going to multiply the probabilities. Okay, so let's start with example 6. It says two regular sided six-sided dice, one green, one blue, are rolled at the same time. For each pair of events below, identify if the events are mutually exclusive or non-mutually exclusive. Okay, so event A, so we've got two events here. We've got event A, rolling a sum greater than 9, and we have event B, which is rolling an even sum. So what you're asking yourself is, can these happen in a single trial? Can the sum be greater than 9, and can it be even? And the answer is yes, it can happen in the same trial, which means these are non-mutually exclusive. You can roll a 10 or a sum of 12, and those are both an even number and a sum greater than 9. Okay, the next example says we're rolling a 3 on the green dice and rolling a 6 on a blue die. Could you do those in the same trial? Yes, you could roll a 3 on the green die and a blue 6. So once again, these are non-mutually exclusive. If you think of that Venn diagram, there's an overlap between these two events. Okay, event A for the next one is rolling a sum of 7, and event B is rolling doubles. So can you roll a sum of 7 and roll doubles in the same event, in the same trial, I guess? So no, you cannot, because 7 is an odd number. if you roll doubles together, you get an even number. There are no doubles that add to the sum of 7. So this one here is going to be mutually exclusive. Okay, let's get into some calculations. Example 7 says a recent survey of a class determined 45% of students watch TV at least once a day, 85% use computers once a day, and 35 do both once a day. What is the probability that the student watches TV or uses a computer? So my suggestion when you're given a bunch of numbers like this is to start putting them into symbols. So I know that the probability that a student watches TV is going to be 0.45. The reason I have changed it to decimals is these formulas only work with decimals. Okay, and then the probability that they use the computer a day, once a day, at least once a day, 0.85. The probability that they do both. So if they do both, we're talking they watch TV and go on the computer. So that symbol that we are going to use there is the intersection. And then what we're trying to find is what is the probability that they watch TV or use a computer. So there are two ways that you could go about this question. You could plug into the formula or you could use a Venn diagram. So I'm going to show you both of those ways. So let's do the Venn diagram first. Okay, so we've got watch TV, play on the computer. As before, we're going to start with the inside of our Venn diagram. So 0.35 do both. From there, that 0.45 and 0.85, they can't go directly in there. We have to subtract the 0.35 from them. So that means that this one here, the watching TV, will be 0.1, so that that whole circle adds to 0.45. And then 0.85 minus 0.35 is going to give me 0.5 for this one. So then when we are looking at or, we are looking, just as set theory, for everything inside of that Venn diagram. So we are going to add up all of those numbers, 0.5 plus 0.35 plus 0.1, and we will get 0.95 for our answer, or 95%. So doing a Venn diagram is a great way to determine your answer, and it does count as showing your work. Okay, let's try the formula now. So if we think about our formula here, we're going to be using probability of A union B equals the probability of A plus the probability of B minus the probability of A intersects B. So when I fill that in, it would look like this with W and C. We would say the probability of W union C equals the probability of W, watching TV, plus the probability of using the computer minus the probability of W intersect C, doing both. Okay, so we would fill that in, 0.45 plus 0.85 minus 0.35. And we would get the same final answer. So you choose which method works best for you. Even better, do both of them, and then you'll know for sure. Next example says the probability that Rob wins a video game is 0.345. The probability that either Rob or Sue wins is 0.617. The probability that both win is 0.224. What is the probability that Sue wins? So just like the last question, there's a lot of information here. So let's represent it using symbols. So the first one says the probability that Rob wins is 0.345. The next one says the probability that Rob or Sue wins is 0.617. Next one, the probability that they both win, Rob intersects Sue, is 0.224. What is the probability that Sue wins? So once again, two different ways that we can tackle this problem. We can use our formula or we can use our Venn diagram. So let's do the Venn diagram again first. We've got Sue. Let's do Rob first, actually, because I did him first. And Sue. We have the intersection as 0.224. We know that Rob is 0.345, so we need to take 0.345 and subtract 0.224 to figure out that Rob himself is 0.121. Okay, so here's where this one's a little bit more difficult. We know that all of this inside needs to add to 0.617. So to get this, the Sue, we are going to take 0.617 and subtract 0.121 and subtract 0.224. Okay, so if I type that in my calculator right, I got 0.272. So that means that the probability that Sue wins is 27.2% or 0.272. Okay, once again, let's try it with the formula. Probability of R union S is equal to the probability of R plus the probability of Sue minus the probability of Rob and Sue. So now when we plug things in, we have a bit of an equation to solve. So when you solve this equation for the probability of Sue, you'll end up doing the exact same calculation that we did on the other side to get that 0.272. So first you would take 0.345 and minus 0.224, and then you would subtract it from 0.617. Okay, so I just verified that on my calculator, and it turns out I got different answers. So that made me think, okay, what happened on the previous question? So I got 0.496 when I solved this equation. And the reason that I didn't get that on the other side is because I forgot one very important fact, and that is the fact that when I'm looking at the probability of Sue, I'm looking at both of those. So I need to take that 0.272 and I need to add 0.224, and then I will get the answer. So 0.272 plus 0.224 is 0.496. All right, we have two more questions left. Example number 9 says the probability that Sean makes a free throw in basketball is 0.45. the probability that Emily and Sean make a free throw is 0.2. What is the probability that Emily makes a free throw given that these are independent events? So we know the probability that Sean makes it is 0.4. We know the probability that Sean and Emily make it is 0.2. And we are looking for the probability of Emily. So if these are independent events, our formula is going to be the probability of Sean and Emily making it is equal to the probability of Sean multiplied by the probability of Emily. So subbing into our equation, we're going to have 0.2 equals 0.4 question mark or probability of Emily. So to solve for the probability of Emily, we are going to divide both sides by 0.4. So our final answer is going to be 0.2 divided by 0.4, which is 0.5. So there is a 50% chance that Emily makes her free throw. Example number 10. In an escape room, the probability that a group will request a hint is 0.68. The probability that a group who have requested a hint will unlock the room is 0.6. The probability that a group who did not request a hint will unlock the room is 0.35. What is the probability that the group will unlock the room? So if I think about this question, I can see that there's two ways for them to win. They could win it by getting a hint, or they could win it by not getting a hint. So this question, there are lots of ways we could tackle it, but the way I would suggest would be a tree diagram, right? The first thing in the tree diagram basically is determining did they take the hint or did they not take the hint? Because I read right at the beginning that the probability that they requested a hint is 0.68. That means that 1 minus 0.68, which is 0.32, they will not request a hint. So 68% of the time they'll request a hint, 32% of the time they will not. From there, they could either win, they could unlock the room. I'm going to put unlock instead of win. Or they could lose. They could not unlock the room. Okay, and that could be whether they got a hint or not. Okay, let's place the appropriate probabilities in there. Okay, so it says that if they have requested a hint, it will unlock 0.6. So 0.6, which means 0.4, they still lose. And then the probability a group who did not request a hint will unlock the room is 0.35. So 0.35. And then remember that those are complements of each other. So 1 minus 0.35 is going to give me them not unlocking the room. So the two outcomes that we care about are them unlocking the room based on the fact that they could have either got a hint and unlocked the room or not got a hint and unlocked the room. So my final statement or my final calculation is going to be 0.68 multiplied by 0.6 to unlock the room, or they had no hint and still managed to unlock the room. Okay, remember to use your words and or appropriately here. Okay, when you type that in your calculator, you will get the answer 0.52, which is 52% of the time they will unlock the room.